Okay, let's give them 2 minutes. Okay. So the vector form of Coulomb's law. All right. The force exerted between 2-point charges has a fixed direction, which is a straight line joining the two charges. Hence, the force can be expressed in the form of vector. So look at this now. 2-point charges, Q1 and Q2. The force on Q2 due to Q1, F2, is Q1, Q2 over 4 pi epsilon naught R square AR, which is the unit vector in the direction of the force from 1 to 2. And of course, we already know how to calculate the unit vector. The unit vector is the vector over the magnitude of the vector, as we know. So here is the vector. R12 over the modulus, which is the magnitude of R12. Vector R12 is vector R, it is the location of R2 minus the location of R1. So this is the F2 is the force exerted on Q2 due to Q1. So the force exerted on Q1 due to Q2 is the same except the direction of the vector. the unit vector R12 is merely the opposite or the reverse of the vector R21. So R12 is minus R21. So A12 is minus A21 is minus A12. In other words, for 2-point charges, F1 and F2, F1, vector F1, are the force F1 on F2. Am I getting it right? The force F1, which is the force exerted on Q1 due to Q2, is minus F2, which is the force exerted on Q2 due to Q1. Did I say that right? Or vector F1 is minus vector F2. Now, so here you go. F1, F2. For 2 positive charges, so like charges repel. Unlike charges attract. Okay. Now, if you have a system with endpoint charges, say you have charge, charge, charge. So this is Q1. This is Q2. Q3. Q4. The force on Q4 will be the sum of the forces exerted by each of the other three charges on Q4. In other words, so it would be a summation of the force exerted by all the other charges, which give you the total force on Q4. Now, what is the electric field intensity?
Sir, it has something to do with the amount of charges in a field.
The amount of charges
So isn't that the same as electric field strength? So
similar.
So then it would be something to do with the voltage, like
Hmm?
the
All right, look at this. Now, if you okay, let's see how they explain it.
Sir, I think it has something to do with the force that a charge experiences when it's placed in a electric field or something like that.
yes, like the individual effect charge exhibit in relation to another charge.
Okay. If you think of a force, right? The intensity of a force would be the force per unit area, right? No.
The intensity, sir?
Yeah. What would you say the force? What would you say the intensity if a man thumping on your chest? What's the intensity of that force? All right.
The force per unit area, sir.
Right. So, but in the case of electric field intensity is the electric field per unit of charge. So look at it this way. Consider a point charge Q1 here. And you have several in a spherical coordinate system. So if it is in the middle here, if you go in any direction from Q1 outwards, right? You should get the same field strength, right? You agree? The Q1 is here.
Yeah.
So if you go at a constant radius anywhere away from Q1, your field strength should be the same. So then, if any other similar charge Q2 is brought near Q1, at that radius, Q2 experiences the same force. All right? As long as you're at a constant radius from Q1. Does there exist a region around a charge in which there exists a region around a charge in which the charge exerts a force on any other charge which is of the same intensity. So this region where a particle charge exerts a force on any other charge located in the region is called the electric field of the charge. So Q1 is located here. Anywhere on this radius, you have Q2. You're experiencing the same force due to Q1. Right? So these lines radiating from Q1 is called electric field. And again, we go back to the equation. This is your force. Now the force per unit of charge is the force is the Coulomb force divided by Q2. And that is called the electric field intensity. So force on Q2, F2, is Q1 over Q2 over 4 pi epsilon naught R12 AR. Force on Q2, or the electric field intensity on Q2, due to Q1 is simply Q1 over 4 pi dot times the unit vector. So that is what is known as the electric field intensity, E. I don't know if I explain it good enough, but it will come out when we do some examples. So this is your force. This is your electric field intensity. Let's do an example. So I have your calculator ready. All right. So first thing, find the force exerted by Q1. Q1 is 1 microcoulomb. It's located at coordinates 3, 3, 3. But you want to find that force exerted on Q1. On Q2 by Q1. Q2 is 10 nanocoulomb located at 693. So take a first crack at it, and then we go through the answer. I'm gonna call on you, so you better be doing it.
Sir, which one? What exactly do you want to historical, sir? Damn, so it's gone.
I hear you coming. What was that question?
Oh, so I was asking what exactly we're supposed to be working out.
You read the question?
And yes, sir, and you just got down to the end, so I was a bit confused there. So we just got, oh.
That shouldn't be taking any more than 5 minutes now, so. Anyone ready?
Sir,
Yeah.
so trying to get the process correct. So it's you consider you move from Q1 to Q2, so you would add the vectors Q1 plus minus Q2 to get the position vector.
The position vector would be position Q2 minus Q1. Position Q2 minus Q2 minus position Q1.
So when it says the force exerted by Q1 and Q2, you consider moving from Q2 to Q1 instead of Q1 to Q2 for the position vector.
From Q1 onto Q2. So you are Q1 and you're pushing on Q2. all right. So I'm gonna restart. Okay, so Mr. Brown. Good morning, Brown.
Yes, sir.
Oh, I'm so sorry, ma'am. Yeah. So when you sit down there, I say, let me see how we might call Mr. Brown.
Yeah, I was checking the participants.
Yeah. All right. Let me see your attempt.
Sir,
What's your attempt? How you?
I didn't attend. This was my first class, and I joined late, so I didn't attend.
Okay. Who have an attempt? Mr. Williams. Patrick Williams.
Afternoon, sir. What? I joined the class late, sir, so I don't know what's happening.
When you say join the class late, you mean today?
No, I just joined the class, yes. This time kind of rough for me, sir, because I work during this time. So I just get a little break, so I decided to come in the class because I'm on lunchtime now. But it's normally rough for me during this time of the day.
You can't take, you can't sign up for a class during your work hours unless you get permission.
Well, there was no other choice, sir.
But you're gonna feel then.
I'll try my best not to.
Anyone can make an attempt.
Sir, I started by finding the position vector by, as I said, to use position vector Q2 minus vector Q1.
Mm-hmm.
And yeah, so the result was 3ax plus 6ay. And to get the unit vector was to divide that by square root of the 3 squared plus 6 squared from the position vector. And got ax over root 5 plus 3ay over root 3. Or I can say ay over root 3. And I was wondering,
So this is your 6 minus 3 ax,
this
9 minus 3 ay, 3 minus 3 az. So it's 3ax plus 6ay. So your unit vector, so this is your R12, 3ax, that is the vector between Q2 and Q1. This. Now, your unit vector, A12, is this vector divided by the magnitude of the vector. The magnitude of this vector is 3 squared plus 6 squared, the square root of that. So this vector divided by the magnitude gives you your unit vector. So you go back to your equation now. F12 is Q1 times Q2 over 4 pi epsilon naught R square AR. Right? And you must can do that math. Everybody get it?
That's yes, sir. That's the equation I got, sir.
What about the rest of the 22 people? Anybody else? Or anybody having a problem with this? Guess not. Okay. So we need to, okay. So this one now. A 20 nanocoulomb point charge exists at this location. Where must a 10 nanocoulomb charge be located such that the total field is 0 at the origin? Let me help you start this. Go ahead.
So I was just going to make a random yes, sir. So, but so you were saying, sir.
No, it's not a guesswork. This. Make a sketch and put the charge where they say it is. And then work the problem. Let me know when you have an attempt.
As in your calculations and everything, yes, sir.
Yeah, man, it's a calculation problem, you know. Anyone at least try something?
Yes, sir, but we get like a real big value. I know see this wrong.
All right. Let me hear what you did.
Sir, we try calculate how much force the 20 Newton point charge would be exerting at the origin just by itself.
Mhm.
And when I put the 20 Newton coulombs over the 4 pi epsilon times the 3 meters squared, because it's only 3 meters down, and because unit vector the unit vector distance over the magnitude is itself, that would be 1. It was like just that equation, and it came out to 2 times 10 to the 10, and also that round. So I don't know what to do next. So.
All right. So for a zero field at the origin, we must cancel the plus AZ directed field from QP, right? So, as you correctly said, this is only in the AZ, right?
Yes, sir.
So you must cancel that plus AZ direction. Right? So you must place your other charge on the other side of the origin, right? So here's your figure. That's your figure, right?
Yes, sir. That's what I have.
So you must have
Something like that.
Hmm?
Something like that. Yes, sir.
Okay. So then, let's set up the equation then. So E total equal EP plus EQ equals 0. E total is E at the origin. And we said that must cancel. So what's the equation for EP? This, right?
Yes, sir. Yes, sir.
Anybody else following?
Yes, sir. I got that. I drew that diagram also, sir. The one that you showed. So I was just reasoning it out, sir, because in order to get 0, you have to counterbalance the chart, sir. But it's
Right.
so weird too.
So here is the equation that's doing your counterbalancing. Because you have everything for EP. Now you want to find EQ. So you calculate your EP, which is this QP over 4 pi epsilon naught R square AR, which gives you this. With me so far?
Oh, yes, sir. I kind of see where I went wrong.
Everybody see how we get EP?
So there's one
Yes,
question,
sir.
sir. In finding the vector, the position vector, not the position vector, the vector at the unknown charge location. How do you know which direction to move from which to which in terms of which one is acting and which one?
No, man. You remember, you know, we already established that QP is at this location. That's given. All right. We are going to have an imaginary thing in our head now. Because I'm in class, I have to call you back. All right. This is your QP right here. This is your QP right here. That's why I said, first thing you do, you find, you make a sketch and put your QP where it belongs. Right? QP, and you want to find, you want 0 here. So the only way of canceling out this is to have a charge along the CMZ here, along that direction. So you think of it like this. You have this charge acting on some imaginary charge here. And you have a next charge acting on the imaginary charge, and they cancel out. So the force here, or the electric field intensity here, due to this must be equal to the electric field intensity due to this one. So you have everything to calculate the electric field intensity due to this, which we did above. Now you set up your electric field intensity due to this one, right? And your unknown is your Z. So all you have to do is now solve for Z. Tell me if you get it, I may have to go back over it.
We're trying getting the problem wrong, so is to put the math to the getting the position for vector 2. I said Q2 minus the one that we know at P is equal to 0, but not sure.
Huh?
To get to set the I said to set the put the location at the 0, 0, 0 point,
Right.
you would have Q. Well, I believe that you would have Q2 minus Q1, but I see that you have Q.
No, you wouldn't have Q2 minus Q1. You would have E. No man, is the feeling of E, not the charge. Read the question again.
Yeah, you wouldn't have to worry about the vectors. Just to find EP and EQ, find the resultant.
Exactly. So then, we know what EP is. EQ is Q over 4 pi epsilon naught R square AR. We know AR is AZ. So once we set up this is the unknown. So EP plus EQ equals 0, or EP equal EQ. The AZ cancel, so you solve for Z. Get it? Oh, that's the thing. Wait a minute. All right. So
Yes, sir.
So that's the electric field intensity due to a point charge. However, we in the real world, we are not restricted to a point charge. We can have a line charge, a sheet of charge, or a volume of charge. And these charges can take any different shape. So, okay. Essentially, we want to calculate the same things. The force due to the charge and the electric field intensity due to the charge. So let's look at the line charge now. We already did the point charge. So look at a line charge. Here you have a line. And like I say, it can take any shape. And the charge.
Is that like a beam or a solid? Like a solid.
What? This?
Yeah, it's like a beam of charge or a solid.
Like a ring.
Yes, sir.
Right. Yeah, that's like a ring. So a charge is evenly distributed along the circumference or along the length. Right? But because it's a line charge, we don't call it Q anymore. We call it rho L. To denote that it's a line of charge. And this is in coulombs per meter. It's a length. So it's given in coulombs per meter. So rho L is the total charge in coulombs over the total length in meter. So if you want to find the force or the electric field intensity, Coulomb's law remains the same. Q over 4 pi epsilon naught R squared AR. But your Q, if it's a line charge, now is your total charge on the line. So, in order to find your F or your E, you first want to find your total charge, which would be your charge per meter times the total length. All right? Mathematically, it's the integral along the length of dq. With me so far?
Yes, sir.
Yeah.
For the ring that I show you, Q would be the integral around the ring dq. Okay? So, which would be, in that case, would be 2 pi r. But like I said, you have to appreciate the mathematical expression because it don't necessarily have to be a circle like that. It could be a square, it could be anything. So it would be the integral around the total length times there. Let me restart. So let's try this. Let me see if you can do this. We'll finish this.
So what do you do with the x squared? No, when you integrate, you would get 30. Trying to
Mhm. You have a charge per meter, and you have the length. What's the total charge?
charge per meter times the length, 30.
So you beat up your head for one. Give me rho L equal 3x squared, and L is that along x-axis. Right? So your differential length is dx. Right? So all you have is the integral of this from 0 to 10. Right?
Because we treat it as the same dimensions, so the x and the L.
Mhm. Your DL is dx now. Get it?
Yes, sir.
All right, so that's a line charge. Like I said, you can have a surface charge. No, your surface charge density is denoted as rho s. And your surface can be of any shape. So rho s is total charge divided by the area. So your charge density, surface charge density, is your total charge over your total area. So it's coulombs per meter square. All right. So let's find the total charge from rho s. If rho s was a rectangle, right, it would be length time width times the surface charge density, right? But again, the mathematical expression for finding an area is the integral over the area. So the integral over the surface, ds. That's the area. So your total Q would be your surface charge density times your area. Now, instead of having a surface charge density, you could have a volume of charge. Note, and in all these arrangements, the objective is to first be able to find your total charge in order to use Coulomb's law. So your line charge, you first have to find the total charge of your line of charge to put in the Coulomb's equation. In the surface charge, you first have to find a total charge to put in your Coulomb's equation. You can also have a volume of charge, like a cylinder, or a sphere, or a rectangle, or a cube, right? Where you have in the line charge is rho L, and you have in the surface charge is rho S. In the volume charge, it's rho V. So this is given by coulombs per volume or meter cube. So one is coulombs per meter. The surface is coulombs per meter square. And the volume is coulombs per meter cube. Total charge, Coulomb over your total volume in meter cube. So for the volume charge density, for the total charge in a volume, it would be your integral over the volume, rho V dV. Following me all the way?
Yes, sir. Yes, sir.
See all of that, you see all of that, you see all of that. See all of that. Here gotta talk. Okay. So let's look at this. You have a line of charge. extending from minus infinity to infinity. So it's an infinite line of charge. And you want to find the electric field intensity at some point P. Okay. Say your line runs in the AZ direction. And you want to find your electric field intensity at a point P along the AY. Right. Okay. So let's set this up. We're going to have this line running through the origin. Why we want to set it up like that? Because if it's not on the origin, we can't make use of symmetry. Some X is going to come into play and the Y is going to be some angle. So we're going to have it along the origin. So this is it. This is your line charge. So your DL, your differential length, is dx, dz. Right? You want to find the field due to the entire length. So the first thing you have to do is to find Q for your entire length. So here we go. Q, dq is rho LDL. So Q is going to be the integral from minus infinity to infinity of rho LDL. Your vector. Now, the contribution to your electric field at this point due to this differential length of line is going to be different from the contribution due to certain differential length here. But wherever it is, wherever it is, this is your position vector. All right? And your vector is the hypotenuse of your R and your Z. So here we go. R is the square root of R squared plus Z squared. Careful about that. You're good. No, don't go. Okay. So you get this so far. Your R. Tell me if you get the R. Anybody here?
Oh, so this is the line. The line chart from the point charge. The line charge being at 0, 0, and Z. And the point charge being at P. So
No, there is not. There's not no point charge there.
Yeah.
That's where you want to calculate the electric field intensity due to the line charge.
okay.
And I'm saying it, your line charge runs along the z-axis from minus infinity to infinity. So you want to calculate E at this point. So if you take a differential length here, your R will be the Pythagoras here. This square plus this square, the square root of that give you R, which is all that I'm saying here.
Following, so
You follow that?
yes, sir.
So your electric field intensity due to that small length DE, this small length here, DL. We call that DE would be this over this. Which would be equal to this. So your total electric field would be the integral from minus infinity to infinity of this. And when you work out all that math, it comes down to this. So that's the electric field intensity due to an infinite line charge. Question.
So when would the infinite line charge come into play? So
Huh?
would you can is that like when you're dealing with ground or something you consider, well, is it an ideal situation? So
Exactly, it's the ideal situation. You wouldn't have an infinite line charge, but you understand the practical, you'll have to have this theoretical understanding. Let's look at an example. I don't want that. I don't want that yet. That I don't want. All right. Okay. Let's do this problem. Make sure you record it in case we don't finish it by the end of the class. So when you get something for part A, let me know.
Excuse me, sir.
Yeah.
Where can I find the recordings of the classes?
Oh God. You're in the group?
Yes, sir.
It's usually posted in the group. Ask Mr. Thompson. You're the gentleman that come in for the first time?
No, it's my second class, sir.
Just asking that one. Ask Mr. Thompson. Or go in the group. It usually is posted in the group.
Mr. Thompson, who is Mr. Thompson, sir?
Yeah, sir, should I send him the link now or after class when posted?
Whichever way will suit him best.
It can wait until the end of class or you need them now?
Whenever I can send them one.
Cool.
All right.
Okay, here what I wanted to do. Because we'll finish in 5 minutes. So finish this problem for next class.
All right, sir.
Mr. Thompson, I would like those videos as well. Here, please.
All right, I'm going to repost the link in the group.
All right, no problem.
All right.
Well, check with your classmates. Some of them get it.
All right, sir. So the book and the solution and everything in there, sir.
Which book and which solution?
The one I have up there now.
I'm teaching from this. Don't you have a text in the syllabus?
No, sure not, sir. As I tell you, sir, we never get something.
Yes, you do. You do.
All right, sir.